Alright, we're going to start off by just doing kind of a quick recap of last day. And so what we did is we looked last day at a velocity time graph. And it was a linear relationship, meaning that it has a uniform acceleration. And from that velocity time graph, we got an acceleration equation, which represents the slope of the line. We also looked at the area underneath the line, which was displacement. And we looked at those two equations, and we ended last class by taking these two equations and looking at how we could substitute one equation into another in order to eliminate a variable. So before we get into just reviewing that and the equation that you should have come up with, we're going to spend some time just reviewing, why are we doing this? Like, why are we going to eliminate these variables? So, in any kinematics equation, what you're going to find is you're going to have four of these variables. So final velocity, initial velocity, acceleration, change in time, and displacement, which are all come from those two equations, acceleration and your displacement. You have 5 variables there, and in any given question, you will encounter 4 of those variables. Now, when you encounter those 4 variables, 3 of them will be pieces of information that will help you solve the question. These will be pieces of information about, initial velocity, or final velocity, or acceleration. And then in the question, as you read through it, you will have to solve for a 4th piece of information. And as you go through it, you'll realize that one of the 5 variables won't be present in the question. And the one that's not present in the question, or the one that is not needed in the question, needs to be eliminated in order to solve the problem. So for example, a question may give you information about initial velocity, time, and acceleration. So those are your 3 pieces of information. That would be the data that is given to you in the question. Then it would go on and maybe ask you, okay, well, find the displacement of the object. And then as you read through it, well, now we got 4 variables, and what's missing from this is your final velocity. It's not mentioned as a piece of a calculation, and it's not what the question's actually asking for. So what we do is then we develop an equation, or we use an equation that does not need final velocity. So last day I asked you to take the acceleration equation and substitute it into your displacement equation, and to come up with an equation that eliminated final velocity. And that's kind of where we left off in the class. So you kind of worked through that, and you had to go back and start thinking about, okay, well, how does this process of substitution work? And how do we eliminate this final velocity? And again, that's the goal of that particular substitution. We want to get rid of these variables. So your first step in substitution would have been taking your acceleration equation, so that's the slope of the line, and then you had to rearrange it to find the value for VF, or what VF's equivalent to. And so what you would have done is you would have taken your final velocity, and then that would have been equivalent to taking your initial velocity plus your acceleration and multiplying it by time. So that would have been your first step in the process of substitution. You have to solve for that VF using your acceleration equation. Now, once you got your rearranged equation here, so that was your VF equals VI plus acceleration times time, you're going to substitute it in for your VF. So that essentially eliminates the VF, your final velocity, from your equation. And so you were left with, two VIs, an acceleration times time, and a time on the outside of the bracket, and then a half on the other side. That you could use. You could go through that and use that as your equation, but that requires more steps. And the more steps you do in a kinematics equation, the more chance you're going to make a mistake. So you want to take that equation and you want to simplify that. So you want to take your time and then you want to multiply it through, and then that's what gave us the t squared. So t times t is t squared, and then t times vi, that's where we got our delta t with our vi. You would have also collected your like terms, and that's why you would have ended up with 2 vi. And then when you multiply your half through, that eliminates the 2. So that one disappears because we divided it out. And then the half also gets multiplied by your acceleration times time, and that's why we have a fraction now. So then in the end, this is the equation that you would have come up with, and that equation is eliminating final velocity. So you would use that equation if you read through a question and there was no mention of final velocity, and the question wasn't asking you to calculate final velocity. So then that is the equation that you would use to go and solve any one of those 4 variables that are involved in that particular equation. Now, the reason we went through that process the other day and why we talked about it is because I want you to understand where these equations come from. All the kinematic equations come from a velocity time graph. They originate with the acceleration equation and your displacement equation. And the other 3 equations that we are deriving are coming from the process of substitution. And that process of substitution is necessary because depending on the question, there are certain variables we need to eliminate from the equation. So if you look on page 44 of your textbook, so you can get your textbook out now. If you look on page 44, you're going to see a chart, and that chart outlines all the kinematic equations that are going to be needed to solve these kinematic problems that you're going to start today. So the middle column here goes through the 5 equations. So the first one is your acceleration equation here. That's the one that was the slope of the line of the graph, of your velocity time graph. This one here is the one that we just derived. That's the one that you were trying to derive last day that eliminates final velocity. These equations here are the area underneath the line of a velocity time graph. So that's looking for the displacement. And the last 2, these 2 here, are 2 more equations that you could derive from substituting your acceleration equation into your displacement equation. And you're going to derive 2 more equations that help eliminate 2 other variables, which is what the last column focuses on. Each of these are the variables that are eliminated with the corresponding equation. So the first one eliminates displacement, second one eliminates final velocity, second one eliminates acceleration, The fourth one eliminates time. And the last one is initial velocity. So again, if I read through the questions and I don't need certain variables, then this chart helps me organize what equation I'm going to need to use. Now, yeah, you're eventually going to need to memorize these equations, but what you'll find is that because you're going to use the equations so many times, you're going to work on so many practice problems that you're going to know them. It's like chemistry and the periodic table. We never ask you to memorize the periodic table, but because you get used to using it so many times, you just get familiar with the location of things. So yes, at first these are going to seem very foreign to you, and you're going to have to look at this chart, and as you practice more and more, you'll just get more familiar with them, and you'll find you will just automatically memorize these as you go through these worksheets. Now, what we're going to do now is go through a couple practice questions, and I'm just going to emphasize the process that you need to go through in order to solve these questions, which is the most successful process, and it helps you figure out which equation that you're going to use. So we're going to read through the question, and this question is written down in your notes already. You just want to highlight a few things as I'm going through it, that just to draw your attention just to small things, and that's what you're going to find with kinematic word problems. You have to practice each one because each one has a slightly different wording and meaning. You just got to be used to those different types of meanings as you interpret the questions. So in this question we got Ben Russian is waiting at a stoplight in his car. When the light turns green, Ben accelerates from rest at a rate of 6 meters per second squared for an interval of 4.1 seconds. Determine the displacement of Ben's car during this time period. So, as we look through this question, the first piece of information you want to look at is, well, he's waiting at a stoplight in his car. Well, when you wait at a stoplight, you have no motion. That means you have stopped. So this would be, in this particular question, that would be his initial velocity. Right? He's starting from a rest, or he's starting from a stop, and that means that he's not in any motion whatsoever at the beginning of this question. Then you read on, the light turns green, Ben accelerates from rest, so again emphasizing from a start, or sorry, from a stop, and now he's accelerating at a rate at 6 meters per second squared, right? So that's his acceleration. And then he's going to go for a time interval, so a time interval of 4.10 seconds. So that's your change in time. So now you have your three variables, right? That's information about your three variables, and the question goes on and asks you to figure out displacement. So, you've got 4 of the 5 variables now. The one variable that you don't need is final velocity. So that would be the equation that we just derived. So we're going to go through that. I'm going to write out the process of how I think you should attack these questions or address these questions so you're more successful. All right, in this question, you're first going to write down your given. All right, so we've talked through that in the question itself. So we had acceleration equals 6.00 meters per second squared. Really important that you write down all the significant digits. Make sure you write down the units. And in this case, it doesn't give you a specific direction. So if that is the case, then you can write down in square brackets beside it, forward. Right? So just think of a car forward and backwards. It's a one-dimensional motion. Then the time was also given to us, so that was 4.10 seconds. Again, important to include those significant digits because in the end you want to make sure you're rounding to the correct number. Then we also know that initial velocity is 0. That is an exact number, so we don't have to worry about that in our significant digit count when we do our calculations. The question then asks us, okay, what is the displacement of the car? So that's our question. So again, if you look at it, we got those 4 variables. We have a 5th variable that's involved with the velocity time graph, which would be final velocity, but the question doesn't mention anything about it. It's not asking you to solve for it, so you can eliminate it. So you'd go to the chart on page 44, and you're going to go through the equations, and the equation that you're going to use is the one that eliminates final velocity, which is going to be displacement equals VI times time plus acceleration t squared divided by 2. Now, this little vector symbol here really should be over VI and acceleration. I am okay with you just putting it on the first one. It defines that we're dealing with vector quantities, and you don't have to worry about going back and making sure that you have your vectors written on each one of those. So put it on the first one, and then you can just carry on with your equation. So we're going to fill in our numbers now. So we're going to have our displacement equals 0 times 4.10 plus 6.00 4.10 squared divided by 2. Now again, this gets eliminated because it's multiplied by 0. We're dealing with 3 significant digits here, 3 significant digits here, so our final answer is going to be 3. This is an exact number, so we don't have to worry about that. And so when we write this out, we're going to go have displacement equals, and I'm just going to write down 50.43, and I'm just putting down the number because that is a number that if I was to carry that information onto another question, I would use the unrounded number. So this would be my extra digit. I would underline that just to know that I really have 3 significant digits, but I'm going to carry the extra one so I don't have any rounding bias. The question's actually asking you for the final displacement, so if that's the case, then I'm going to write 50.4 meters bracket in my direction forward. And again, I prefer that you block that off, highlight that, so then I know that's your final answer, round it to the correct number of significant digits, and also you have your direction involved. All right, our second practice problem. What I'm going to do is I'm going to read through it, I'm going to highlight a few things, and then if we could just stop the video for a few minutes, let you give it a try yourself, and then I'll explain the solution after you've given the try yourself. All right, so Ima Hering approaches a stoplight in her car, which is moving with a velocity of positive 30 meters per second. The light turns yellow. Ima applies the brakes and skids to a stop. If Ima's acceleration is negative 8.00 meters per second squared, determine the displacement of the car during the skidding process. So if we look at this, there's a few key pieces of information and a few key things you want to interpret from this question. So they're approaching a stoplight. The car is initially moving 30 meters per second. So that's your initial velocity. And you'll notice that in this question, they're using a positive to define the motion of the object. So the positive we could define as moving forward. As we read through the question, you'll see that applies the brakes and skids to a stop. So we know that the stop here would be your final velocity. The acceleration of that stop is negative 8.00 meters per second. Again, you'll notice that there's a negative sign here. So the negative in this case indicates direction. So this acceleration would actually be written two ways. You could either be written as negative 8.00 meters per second squared forward, which really means that it's going backwards, or you could just write 8.00 meters per second squared backwards. When you're calculating, the positive and negatives are essential though, because mathematically that's the way we show the direction that the object's actually moving. So I'm going to let you work through that, give you 3 or 4 minutes just to work through it, figure out what equation you're going to use, do your calculations, and then I'll show you the solution for that problem. Alright, the solution for example problem 2, and we're going to write the given, so let me just change that color there. So we got the given. As we stated in the setup of the question, we got initial velocity, which is going to be 30.0 meters per second, and that's going to be forward. Again, this in the question was positive, and then that indicated the forward direction. We then have an acceleration, which equals negative 8.00 meters per second squared. And again, we're going to say forward, which really means that it's backwards. It's going the opposite way, but we're defining the direction the same way to make sure that the positive and negative are indicating opposite directions. Now again, mathematically, we want to include the positive and negative into the actual question. And the other piece of information it gives you is it states that it is coming to a stop. So that's going to be 0. Question asks for displacement. So if we go through those 5 variables again, we have 4 of them here. The one that's missing is time. We don't need time because time is not involved in any of the information, and time is not what we're trying to find. So you're going to look on page 44 and you're going to come up with an equation, and that equation that's going to solve this question is going to be VF squared equals VI squared plus 2 times acceleration times displacement. Again, I'm just going to put the vector symbol on the first variable just to indicate that it's a vector problem, and then we're going to plug in our information to solve the question. Again, you can rearrange the equation beforehand, you can rearrange it for displacement, or you can put your numbers in and then calculate it. Doesn't make any difference to me what method you use. Just choose the method that you're used to using, the one that you're the most successful with. So in this case, I'm choosing to rearrange it. So displacement equals Vf squared minus Vi squared divided by acceleration 2 times acceleration. And again, that's going to be a displacement that we're concerned with. So I'm going to plug the numbers in. My final velocity is 0. My initial velocity is 30.0. I'm going to square that. And I have 2 times negative 8.00. And now I can calculate my answer. And it's going to be 56.25 meters. It comes out positive, and again, this is why it's essential to make sure you have the positive and negatives in the right spot, and that if you just go back to your VF and VI, you have the correct order there, because that makes the numerator negative, the denominator is negative because we have a negative 8, and that is going to give you a positive displacement, which makes sense. The car is still moving forward as it's slowing down. And so our final answer is going to be our displacement equals 56.2 meters forward. And again, I would block that just to highlight that that's my answer. This one would be used as an extra digit there, just if I had to do some more intermediate calculations. So those are your 2 practice questions. Again, your success in this in kinematic work problems is practice, 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 practice. You have to get exposed to the different types of questions. So to do that, there are some textbook questions. So for your homework, you will be working on pages 46 to 47, numbers 1 to 5 and 7. Plus kinematic, if I could spell it correctly, kinematic worksheet number 1. So you have the rest of the class to work on that and work on your textbook questions. We will take questions up next day. I'm going to pick a few questions that we're going to highlight. I will also be making some more videos just on some solutions, right? So I'll show you the solutions, I can work through them with you, and then so if you need to go over things that we didn't quite go over in class, they'll also be on Google Classroom. All right, so good luck on those questions, and again, when we come back next day, we will we'll start working on those kinematic worksheets. Just as a heads up, today is a Monday, so you will be having a quiz on Friday, and that quiz will be on position times, velocity time graphs, and just general information from those graphs. I will go over that on Wednesday, but just to kind of give you a heads up, that is coming up on the Friday. All right, so good luck, and we'll see you on Wednesday.